Good afternoon, everyone, and welcome to our Mechatronics Education Community webinar. Today we invited Dr. Brandon DeHart from the University of Waterloo, and he will give us a tour of their new research, teaching, and training facility, the Waterloo RoboHub. My name is Susanna Fabusheva. I'm from Quanser, and together with Dr. Nima Lotfi from Southern Illinois University, Edwardsville, we will be your hosts and webinar moderators today. And now I would like to pass the microphone to Dr. Lotfi to talk briefly about our mechatronics community.
Thank you very much, Susanna. Hello, everyone. As Susanna mentioned, my name is Nima Lotfi. I'm from Mechanical and Mechatronics Engineering Department of Southern Illinois University, Edwardsville. And I am one of your moderators today. So this webinar is one of the many webinars that we have had, and we will continue to have in the webinar series on mechatronics education innovation. So this is one of the activities that we as a community of mechatronics educators have been undertaking. So our community started back in 2016 after a workshop at NYU Tandon School of Engineering. It was officially launched in March 2017, and since then, our first activity was creating a website, mechatronicseducation.org, which is comprised of announcements, news about the field of mechatronics and robotics, a forum, and also a repository that contains material related to mechatronics and robotics education. As a follow-up activity we started this webinar series. We have had multiple webinar series from well-established mechatronics programs around the world. And since last year, we have also started holding online workshops. Holding workshops in conjunction with technical conferences. So we've already held 3 workshops. One in ASME DSTC 2018, Robotics Summit and Expo 2019, and ASWE 2019, which was last week. And we are going to have another workshop next in September 2019 in Lawrence Tech. So in these workshops, we have brought together educators, professionals from in the field of mechatronics and robotics education, and brainstormed about the future of this field. So if you want to be in touch with the community and learn about our future activities, especially our last workshop in Lawrence Tech, make sure to subscribe, to go to this website, register, to have and create your account there so that you're in the loop of all our activities. So as Susanna mentioned today, we are honored to have Dr. Brandon DeHart from University of Waterloo. The title of his presentation is the Waterloo RoboHub. What is it, what it is, and why you should care. So let me tell you a little bit background about Dr. DeHart. He's the manager of the Waterloo RoboHub and the sessional instructor at the University of Waterloo. He has been working with mobile and legged robots for over 10 years with a research focus on balance and gait for bipedal robots. In his role as the manager of RoboHub, he's responsible for the purchase, installation, configuration, and testing of all new robotic platforms and the deployment of any additional essential equipment such as the control center, safety systems, and environmental variation system. He also coordinates and supervises day-to-day activities being undertaken by technical staff, students, and researchers at the facility. In general, his research spans a wide range of topics connected to robotics, from tensegrity structures and bio-inspired robot design to interactive architecture and morphological computation. Starting early in his academic career, Brandon has always strived to work on solving problems that will enable the widespread use of robots in entertainment, education, and exploration. We're excited to have Dr. DeHart as our presenter, and I am looking forward to hearing your presentation, Brandon.
Hello, everybody. My name, as introduced, is Brandon DeHart. I'm the manager of the Waterloo RoboHub, and I'm also a sessional instructor here on campus in mechatronics, electrical computer engineering, and mechanical, depending on the term. Today, I'm going to give you a bit of an introduction to the University of Waterloo engineering program, just at kind of a high level, and then talk as well about what the RoboHub is and why you should care. And specifically try to link in as much as possible to the education side of how what we do and how we do it improves the education for undergrads, graduates, and beyond. So we'll get going. So to start off with, Waterloo Engineering is Canada's largest engineering school. As you can see, we have almost 8,000 undergrad students and over 2,000 grad students and over 300 faculty members. And almost an equal amount of staff supporting that. What that means is that we can do things that other schools in Canada can't really do because we have that critical mass. And one of the things that we do well is kind of this innovation umbrella that everybody kind of talks about. And the main three reasons that we can actually achieve that is because at the University of Waterloo we have an inventor-owned IP policy, which means that whether you are a staff member, a student, a professor, a postdoc, whatever it is, if you come up with something, it is yours. If you'd like to loop in the university and have them take care of patenting or helping you generate funds, things like that, then you can give away some of that IP if you'd like to, but there is no requirement for you to do so. So anything you come up with, invent, create, etc., is yours. And because of that, we have a very strong startup culture, which I'll talk about on the next slide. Where professors are part of startups, students who are coming out of undergrad, coming out of grad studies, immediately start up companies and can create things and use the developments and unique pieces that they've developed to start companies in the area and abroad, really. The other two pieces of that are the transformational research, which the RoboHub is a big part of, and we have a huge research program which is just growing exponentially. With a very heavy focus on engineering. We have significant investments both from the public sector and the private sector in effectively all fields of engineering across the board, because the University of Waterloo was started as an engineering school that right from the get-go wanted to be connected to industry, which ties into the third point of having a heavy emphasis on experiential education. So everybody who comes in to do an engineering program must do at least 5 co-op terms, 6 or more if they choose to. So potentially when you finish your engineering undergrad here at Waterloo, you could have worked for 6 different bosses at 6 different companies doing 6 different things, and you have a reasonably good idea of what you enjoy, what you don't enjoy, what you're good at, maybe not so good at, and the kinds of technical expertise that you might need for the types of jobs that you want. It also prepares our graduates very nicely for the outside world. And I'll just give you a couple of details about that before I move into the actual meat of the presentation about the Waterloo RoboHub. So just a few facts here. On the entrepreneurship side and the startup side, we have hundreds of entrepreneurs that have raised billions and billions of dollars as of a couple of years ago. And that number has obviously gone up since then. And we have Velocity on campus, which is actually the largest free student incubator in the world, with a relatively high survival rate, especially for startups started by undergraduate students for the most part. And we are also in kind of top lists for being VC backed, creating unicorns, creating jobs, all those kinds of things. So we are very much involved in our community, involved in that side, which then leads to a lot of people coming back from those startup companies or even from larger companies to talk to us about both entrepreneurship and about the kinds of research and education that we provide. So we actually have something that we're working with a little bit called reverse co-op, where people in companies, executives, managers, etc., can come back to the university and learn about AI and how it can affect their company, or learn about robotics and how they could potentially put a collaborative robot on the desk, either their desk or the desks of their employees, and how that might augment the capabilities of those employees. And then the last kind of general slide, that co-op is extremely valuable. It is a huge part of what we do here at Waterloo, particularly in engineering, but actually across the board. Most of our programs at Waterloo have a co-op component of some kind. Many of them are optional as opposed to mandatory, like it is in engineering. But it gives everybody kind of that good basis so they can take that and move into the world with some real experience at companies, like I said, with multiple bosses, things like that. And a lot of students coming in actually choose Waterloo because of our co-op program, because we are, like it says, #1 in Canada and #4 in the world for employer partnerships. And because of that, we also have a lot of industry connections coming in who then work with our researchers, work with our professors and instructors, lecturers, to incorporate the real world experience into the educational system and into the research program. So it's very much kind of an interconnected thing, which you'll see as I kind of go through the slides about the RoboHub specifically. Okay, so the RoboHub, Waterloo RoboHub, is a state-of-the-art robotics research and training facility with a globally unique fleet of robots. What does that actually mean? It means that we have built a relatively large room with many robots in it, lots of different types of robots, which you'll see in a little bit, which is dedicated to research and training. So it's not owned by a particular professor, it's not beholden to a particular fund or degree program or department or anything like that. It lives under the Faculty of Engineering, so we're kind of a general space, and we have in any given week anywhere from 6 to 40 or 50 professors and their postdocs, grad students, undergrads, undergraduate research assistants, fourth-year projects, all kinds of things working in the RoboHub. Specifically, the RoboHub is basically working at the intersection of collaboration and robotics. So in any particular combination of those, we are interested in looking at both the research themes, the connections to industry, how it affects education, and how our students and our researchers need to be connected into that ecosystem in order to understand how things are going to work. So that might be how to make robots work with robots, how to make robots work with humans, how to get academics and industry working together on a project. One of the hardest ones is getting professors to work together, and I can say that because I'm not one. Really, it's getting all of those bits and pieces together so that you can look at every level of collaboration when it comes to robotics. And we also work very closely with the AI Institute on campus. We work with the autonomous vehicles team, some of the student teams, lots of different sides of the coin, because we have kind of this central location in a new building, and we also have a mandate effectively to look at all of those connections between collaboration and robotics. What does that look like on the research side? Effectively, we have these 4 key research themes. So obviously we have a lot of robots that are at the early stage of research, so we have to look a lot at the control side, both high level and low level control. So for something like our industrial level full-size humanoid that you can see in the back, the Talos, control is a big part of what we're doing and what we're working on for a system like that. Moving into some of the more common ones like a mobile manipulator or drone, things like that, we look at some of the planning, some of the perception, specifically looking at multi-robot planning and shared perception. So sharing maps between systems, having one robot which might not have a good view or a good set of sensors for a particular thing able to request information from another one. So maybe a ground system doesn't have a good idea of what's in the next room, so a drone will fly in and give it almost like an eyes in the sky kind of approach and share that map, share that information, so that the ground robot doesn't necessarily have to have a full depth camera and all of those things. It can ask for that information from another one of the robots. And then obviously to tie everything together and tie the humans into the loop is that interaction piece. And that is robot-robot interaction, robot-human interaction, both on the interface side, on the control side. How do you actually program it? How do you teach it to do things if you want to run some kind of AI in the back end for vision, for pattern recognition, for motion learning, all those kinds of things. So those 4 pieces are kind of our core pillars that hold everything else up. And in order to look at these types of questions, we actually have acquired a globally unique fleet of over 30 robots. So as you can kind of iconically see here, we have humanoids, arms and legs, we have fixed base arms, we have flying drones of various sizes and scales, we have autonomous vehicles, both indoor and outdoor, and various combinations thereof. So mobile manipulators with 2 arms, mobile manipulators with 1 arm. Some of our drones have multiple sensor suites on them and coordinate with ground platforms to charge, things like that. So a very interesting set of tools that we can use to look at all of these various bits and pieces. So I'm going to quickly go through a few of those. First off, we have obviously the smaller kind of human interaction, social interaction robots on the humanoid side, but we also have industrial strength humanoids like the Talos at the back here. And we're looking at a lot of different things, again, to augment humans. So carrying something with a human, and in this case, there's no actual perception going on. So all of the responses with the table are based on torque sensors in the elbows, torque sensors in the arms. It wasn't actually watching Alex, who's in this video, our humanoid specialist, what he was doing. It was only paying attention to how the table was moving. And the compliance that you can see there is enabled by the torque sensors that are in the arm, in the upper body. So it can fully balance using a lower body controller, which is distinct from an upper body kind of softer controller, where it's only trying to spring its hands back to a particular location relative to its body, as opposed to rigidly holding them firm, which gives you a bit of that collaborative safety, and it gives you a bit more of a sense of, it effectively gives the robot a sense of feel. So it doesn't have touch necessarily, like it's not coated in the skin or anything, although that can be done, but it does have an idea of how hard it's pushing on the world, on people, and how hard they are pushing on it. And one of the reasons we use the small humanoid robots is to map some of the social aspects and the human interaction aspects on the small robots, where we can test it, and it doesn't really matter if something breaks or it swings its arms around. It's not really going to hurt anybody. It can't hurt anybody. And we can map those human interaction lessons that we learn up onto the bigger systems like this one. The next piece is the collaborative robot arms. Here we can see a couple of them. Franca Emeka Panda on the right and the Sawyer on the left, which has been bought from Rethink by Han. But really the similarities here, and we have several other fixed base collaborative arms as well. The big thing is that they have those similar torque sensors, or in the case of the Sawyer, serial elastic actuators, so that they know, again, how hard people are pushing on them, how hard they're pushing on the world. And you can see there's actually a hand on the Panda on the right there, guiding it, so you can actually teach it by dragging it through a set of poses and using buttons on the robot itself to teach it, much like the robots or the buttons that are on the Sawyer on the left as well. So you don't actually need to be a robotics expert to teach these robots whatever task you want them to do. You can bolt it to the table, you can teach it a task, it can do that 100 times, and then you teach it something else. And you can adjust that using a super simple tablet interface right out of the box. And then you can also, for all of these systems, go deeper and deeper as needed to satisfy the educational and research needs of the students and professors and lecturers and everybody who is involved with these systems. So you can have that initial human interface, which is relatively simple for someone where you want to treat this as a tool that gets planted on your desk, and you're using it to do the dull, dirty, dangerous, boring, repetitive pieces of a particular task. So you're effectively treating it as just another tool in the toolbox. And then if you get further into the education side, you can look at, okay, well, how are they doing that? How do we modify that? These are redundant robots, so they have more degrees of freedom than they need, more joints than they need. So how do you figure out what to do with that extra motion freedom? All of these are kind of questions that we're looking at in our undergrad and graduate education programs, particularly in mechatronics. And we actually have a fourth-year design project going right now that we're supervising, where they're trying to figure out a way to build one of these effectively collaborative robot arms with torque sensors and 7 degrees of freedom to get the redundancy at a scale that you can use for education, where every student in the class has a robot, as opposed to something like these where you might have 2 or 3 for a class, if you're lucky. Combining that a little bit, you can get collaborative arms and actually mount them to a mobile manipulator, like these 2 systems, where you can have different types of systems, different types of arms, 2 arms, 1 arm, sensing, potentially there's a camera on board, or in this case there's a remote camera, telling it where and how those things are being connected together. And these will enable you to take those collaborative arms and some of the lessons learned there with having it bolted to a table, and then apply that to, okay, well, now you have a vehicle that is capable of moving throughout a space. So what challenges does that impose? What benefits do you get out of that, right? And there's many different aspects to this. There's the sensory part, there's the perception part of where is the table, where is the robot, how is the arm moving. There's also the controls piece, trying to unify the controls for the mobile base compared to the arm. And figuring out, obviously this isn't interacting with humans, but if you have an arm on a mobile base, like the Movo, the black one that you saw first, how does that interaction actually work? What does the interface look like? Is it voice? Is it a tablet? Do you have, you know, a keyboard somewhere, and that is how you're actually controlling and interacting with it? Because all of those things will change what kind of sensor modalities you need, what kind of background you need to actually program a system like that, and how many layers and what kinds of layers of safety and control that you need to make those kinds of things work. So moving on from kind of the mobile manipulator side of things, we also have a relatively diverse set of aerial platforms. So we have an outdoor system that you saw me adjusting the camera on there, and we have several of those, and we also have several of these Quanser Q drones, which allow us to do a lot of nice indoor research, multiple platforms. We can combine them with ground vehicles and get kind of right out of the box, they work well with their kind of paired ground systems. So we can have them follow each other as it's doing here. We can have one drive the other. We can have all of them be autonomous. And we can look at those kinds of systems. We can have multiple ground platforms, multiple aerial platforms, and generate algorithms and equations and planners and all those kinds of things for these systems that are indoors, and then map those to maybe bigger outdoor systems, for example. And you can look at things like when you're in a GPS denied environment with an outdoor drone, how does that work? Maybe you have a base station on a big mobile system, like we'll see in the next slide, which can carry your power. It can carry a GPS base station or an ultra wideband localization system, something like that. So then the drone only needs to know where it is relative to a ground platform. And the ground platform, if it loses GPS, it knows that it hasn't left the ground, for example. It's not going to fall out of the sky when it loses GPS. It'll just stay where it is or try to find GPS again. So you can use the strengths and benefits of the different platforms together, because we have all of these various types of systems at the RoboHub, to combine and extend the capabilities that you would have with only one or two of these systems. And we can map, much like we can map things from the small now humanoids up to the big Talos, we can map from these Q drones and Q bots, relatively simple to use, very reliable kind of education systems, Q-bot and Q-drone, to bigger systems, outdoor systems, more systems, all of those kinds of things. And one of the nice things about these on the educational side, at least, is that you can run MATLAB right on it. So if the students are already learning MATLAB in the class, which they do in undergrad here, they can directly effectively draw the control system that they want in Simulink, for example, and they can actually run that right on the ground platform or the aerial platform, have them talk to each other, all that good stuff. You'll notice also that these have markers on them, and we will talk in a bit about our indoor positioning system, but one of the nice things about that is that we can use these to validate algorithms that are running either aerial or ground systems for planning, for perception, all those kinds of things, and we can make sure that the maps and distances and all those things that are being calculated, we can verify them with the indoor positioning system, or we can just use the indoor positioning system directly, and we don't have to build in a lot of those additional pieces. So it makes it really nice on the education side that you can mix and match which components any given student or group of students is actually looking at, has to develop themselves. And one of the things that we are doing in the RoboHub is trying to make it so that when a new master's student, let's say, or a new undergrad student comes in as a co-op or something, they can ramp up really quickly on the platform that they need for their particular problem and get right to trying to solve their problem, as opposed to spending a term finding a robot and another term finding funding and another term learning how it works and another term getting it reliably working and flying or driving, whatever it might be. All of those things we are effectively taking care of with our staff and our knowledge and understanding of all the various systems, so that when they come in, they can say, oh, okay, here's a few weeks of instruction and tutorials. Now you're ready to work on your planning problem, for example. And one of the reasons that that's super beneficial is when we go outside. So these are a couple of our outdoor platforms. Our Warthog is actually orange, but it is still amphibious. It's got a bunch of sensors on top, multiple GPS setups, and a Velodyne laser scanner, those kinds of things. And we actually use these systems to both upscale some of the algorithms that we run inside and to do a little bit more of the general kind of dirty or dangerous work that we can look at outside. We can simulate those kinds of things or actually do them outside, because these are fairly rugged systems. And the vast majority of the systems, I haven't really talked about this yet, but the vast majority of the systems that we have all run on the robot operating system on ROS. So because they have that common middleware, generally they can all talk to each other. You can run the same planner on multiple scales of system, things like that. So we're trying to make it really easy for people coming in to understand how to take something that they've learned in class and map it onto a real robot, or how they take something that they've built for a Husky, like the one on the left, and map it up to a bigger system like the Warthog on the right. What changes, what stays the same, and how those things, how and when those things need to be paid attention to effectively. I'll move a little bit, move to a slightly different topic here. So we also, one of the unique things about the RoboHub is that we have Professor Behrad Kamisi here on campus, and he is a world expert on magnetic levitation systems, specifically not like a maglev train where it's very much linear, you have one track and it travels along that track, but actually in 3D localization, 3D motion, 3D levitation of initially micromagnetic robots, and now this platform here is a little bit larger. And I'll give you a few details on that. So this is basically a magnetic table, which is approximately 2 by 3 feet. And there's actually several different types of modules, I guess, that we have for this one. That first one you saw was just purely capable of lifting up and down. It only had one permanent magnet. This one that you see on the right has 3 different permanent magnets in it, so we can actually control the position and the orientation, roll, pitch, yaw, fully with this system. And the way that we do this is actually by using a set of individually controlled electromagnets in this table to modify the magnetic field above the table in order to manipulate how and where these magnets are. And you'll see again those reflective balls, and in the picture in the top, some of the cameras that are used to actually localize those reflective balls there. I'm not going to go through all the details here, but basically the applications for this size of system are for clean room manipulation, things like that, because there's no moving parts where the actual module is. So within this levitation space, within the volume, there's no moving parts, there's no need for grease, or there's never going to be rust, there's never going to be any of those things unless you're introducing those in another way. So effectively you can create a confined clean room and use this to do 6 degrees of freedom, effectively, full 3D manipulation of an object, of multiple objects, as needed. You could also put it in a wind tunnel, obviously, because there's no support system for this. You could actually look at what the forces are, because you can measure that based on the magnetics, pick and place, collaborative operation, etc. So there's lots of different bits and pieces to this. And you could, because it is, again, just permanent magnets in here, have a liquid and have the motion of the actual module itself help you to measure. So you can actually use this magnetic module, this maglev module, as a sensor. So you can look at weights, you can look at density and viscosity and all those kinds of things. And then if we move from this up to the full scale one that we are currently designing and installing. So in some of the previous pictures, you might have seen the tiled floor in part of the RoboHub, which is outlined in that top picture. And basically in there, there's going to be a 2 by 3 meter levitation volume, which is not super deep, but deep enough that you can do a lot of interesting things with it. And we can also have multiple platforms running at the same time. So because we have individually controlled electromagnets underneath the floor, we can actually have them move around independently. We can have them do coordinated tasks. And here, obviously, they're being treated as simple floating systems. But you could do any number of different things with this. Again, reasonable load capacity, 5 kilograms, and moving at a relatively good speed as well. And this kind of larger system, which will be the only one of its kind, because it's being developed and created here on campus, specifically for our space. It enables, like shown here, some flexible manufacturing. You can use it to carry things in a warehouse if the magnetic volume gets longer, bigger, etc. And again, you can do some more of that clean room manipulation, confined space manipulation, and many of the things that the smaller table is also capable of. Obviously, you can do with the bigger table. It's a little bit more challenging because with the bigger table, your resolution on the magnetic field gets a little bit lower, obviously. But the accuracy and the positioning and all those things are relatively the same. And if you want to scale up, it's basically just a matter of cost in terms of how many amplifiers you want, how many electromagnets, etc. Because really they're just analog systems that you can define how strong you want the field in any particular magnet, electromagnet, and then have these platforms that you can localize using whatever system you want, whether it's video or an indoor positioning system or anything else like I've talked about. So getting a little bit to the outside level, in the RoboHub, we also have a few things that enable us to do some interesting work on humanoid gait and measurement, validation of sensors, testing of external robots, all those kinds of things. And the big main one is that we have an advanced Vicon IPS, which can also be used as a motion capture system. We currently have 24 cameras. We're hoping to approximately double that, maybe not fully double, because we also want to put a set on the ceiling so we can use our full volume for collaborative flight and swarm flight research. In tandem with this, we have a control center that we use for real-time fleet management and visualization, so a lot of visual feedback, a lot of details on what kind of messages are passing, what the latency is, all those kinds of things. So you can analyze a lot of the network side of things. We also have a VNA, so that you can look specifically at the wireless information, density, bandwidth, all that fun stuff. The windows actually on the RoboHub are privacy glass, so at the flick of a switch we can turn off all the windows, so that instead of a showcase space where you can see everything that's going on, you can watch research happening in real time, watch the robots moving around, you can turn it off if there's a confidential project, or if you want to create an artificial environment, because once the windows are nominally quote-unquote turned off, you can use those windows then as a projection surface. So you can project an artificial environment, you could project sensor data, information for the people, information for the robots, etc. And we're actually looking at getting some augmented reality and virtual reality components as well in the space so that the people that are in the space can actually see what, for example, the shared map might look like. So if multiple robots are collaborating, they're building a map together, you can pop on something like a HoloLens potentially and look through that to see what the actual robot's map looks like and understand why they're running into an obstacle. Maybe they can't see it, or they think an obstacle is a different size because of reflectivity, or maybe there's a sensor problem potentially. You can see that right away and get that intuitive feeling of, oh, now I know what the problem is, I can fix it. You don't have to dig through a 3D rendering on a computer and try to figure out how those connections work. Sorry. One of the other things we do is we have various fans, stairs, doors, a pile of rubble, etc. So we can do real-world task simulation in the RoboHub and make sure that everything is working how we expect, that the algorithms are working as we expect, and the physical robots are doing what they're supposed to before we then take it outside into a windy environment or try to make it do stairs or open a door, etc. So we can actually do some of that real-world simulation inside, which is especially helpful because we're in Canada, so lots of time there's snow or rain or who knows what going on outside. So it's nice to have a space that we can simulate some of those things that we know is somewhat controlled, and we can verify some of our assumptions before we bring systems like the Warthog or the Husky or some of our drones outside or out into the world to see kind of the real world impact. And one of the big emphasis pieces we have is trying to look at real world problems and find the solutions, and then pass that along through courses, through workshops, etc., to the students that are coming in, the grad students, etc. And the last piece that I'm just going to mention is that because the vast majority of our robots are based on ROS, the robot operating system that I mentioned, We also have an initial version of a multi-master network in development, and we're debating right now how we should do that for robots that are not actually running ROS. So whether we use something like Quark as a backend to hook all of them together, and then that produces ROS nodes for those various things, like the maglev system that we're defining, or if we go to a model like ROS2, where you can have multiple systems and you don't necessarily need a master, they can talk to each other, etc. So we're actively working on that right now. And if any of you are actively working on that, we would be very interested in working with you on that aspect. With that, I think I will close up and say, if you have any questions, please send your questions through the webinar's questions page. Thanks.
Thank you, Brandon, for a really interesting presentation. We have received a couple of questions from the audience, and as Brandon mentioned, if you have more, please feel free to send them through the questions window. We have some 15 minutes to answer the questions. So the first one that we received was about the products, or quite a few are about the products that you have in the Waterloo RoboHub. Do you have a universal robot product?
No, we do not. So on the collaborative robot arm side, we have 2 Sawyers from Rethink, which are now on. We have 2 Pandas from Franca Amica. We have 2 Jackos and a Gen 3 from Canova in Montreal. We have KUKA IIWR14, which is the bigger collaborative robot arm from KUKA. And I think that's it in terms of arms. Because one of the things that we look at for when we're acquiring systems, specifically for when we're acquiring arm systems, is that we like to have the capability to actually measure torques and forces in every single joint, which all of those systems allow us to do. The UR arms do current-based torque sensing, which isn't kind of reliable enough for the kinds of research that we want to do with collaborative robot arms here.
And the most of the robots and equipment that you have is off the shelf, or do you also build robot manipulators or other robots yourself?
So as of yet, other than a few fourth-year projects that we're supporting, which is kind of that capstone project for the fourth-year students here, we haven't built any custom robots. We have customized some of the robots that we bought off the shelf. So some of our ClearPath robots, for example, we've put different sensors on them, or mounted an arm or dismounted an arm, various things like that. We will be, as we move forward, working with Professor Kirsten Dottenhahn, who effectively created the field of social robotics, to see if we might want to develop a new version, a new iteration of the social robot that she worked with at Hertz in the UK. And I have a feeling that some of the professors on campus who work on exoskeletons are going to be leaning on us a bit to potentially develop or modify exoskeletons for them. But part of the idea behind the RoboHub was to be able to figure out, if you don't have someone who can build new robots, develop new systems, etc., if you're buying things off the shelf, how do you make them work together? How do you make them work with humans, etc.? Because if you are a company or you're a smaller educational institution, you're going to want to just buy a robot or several robots, whichever apply to your particular task or kind of goals, and have them play nice together, which is part of what we're trying to develop and create.
Thank you. Do you use any robot simulators such as VREB or Gazebo to test behavior of the robot manipulators?
So because we're working mainly in ROS, we do use Gazebo a fair amount. We are working right now to try to figure out if there is a server-based solution we can use, whether it's AWS RoboMaker or the Construct or what it might be. And all of those use Gazebo or some form of Gazebo, which for most of our robots, because they are ROS native, that's kind of their natural habitat. We have been also looking at VRAP, and I can't remember the other one. But most of the time we're playing in Gazebo Land because we are working with raw-based robots.
Okay, thank you. So a couple of questions now related to the RoboHub operation and structure. How long has the RoboHub been in operation? And do you have any statistics already that can link the outcomes with respect to quality of undergrad education?
So the RoboHub itself, or the whole building actually, the entirety of Engineering 7, which is where the RoboHub is located, we only got access in September. So it's been open for about 9 months now, 10 months, I guess. The official opening was at the end of October, so nominally it's been kind of 6 to 8 months of actual useful operation. Throughout that time, we've been acquiring robots pretty steadily. So I think the last robot that showed up was only about a month ago. And we are finally getting to the point where, other than the maglev system, we're getting close to having all the robots we want, and now we're working on ramping up our kind of environmental simulation and additional sensors, additional cameras, all that kind of stuff. So because we're so new, we don't really have any statistics that we can point at or look to in terms of how impact is affecting, or education is affecting our impact, or vice versa. But we do have requests, it seems, on a weekly basis from undergrads and graduate students, both from our campus and from campuses across Canada, to work with our robots, to come in and kind of get a workshop with us, things like that. And one of the things that I didn't really mention when I was giving the talk is that the idea behind the RoboHub, once we're kind of up and running, which should happen in fall at some point, kind of fully operational, is that we want this to be a resource for all of Canada. Because the lab was started, it was kind of founded with a CFI grant. It was the biggest investment in robotics that the federal and provincial governments have made in over a decade. And we want to be able to share kind of that wealth of infrastructure, the wealth of equipment and experience with everybody across Canada, because we know there's a lot of places where you don't have the space to put up a lab like this, or maybe you don't have the funds to get something like Talos, or some of the bigger systems. You might have one or two. So one of the things we're working on doing to kind of tie a few of these questions together is to actually have a cloud-based system where you can simulate and test behaviors and things like that online, and then you can actually send that, upload it, bring a person to the RoboHub and test it on the real hardware that we have here. We want to make it very much kind of a physical and digital resource for everybody to do robotics education and robotics research.
Thank you. You touched partly on the next question about the RoboHub funding, but on top of the governmental funds, do you also partner with sponsors, or particularly in-kind sponsors?
Yeah, so we do have, there's kind of three pieces to the model for the RoboHub. So it was started by a CFI grant, like I said, which is partially federal and partially provincial, and then partially in-kind. So part of the in-kind came from the university, from the provost's office, and part of the in-kind came from companies like ClearPath and Canova and Quanzer and PAL and those kinds of places where when you use CFI funding to acquire robots, there is an expectation that the company will provide some portion of the cost as an in-kind donation, effectively. We also have funding from the Advanced Manufacturing Consortium, which is an Ontario group of 3 universities, which the university is part of it, and the RoboHub is one of the 4 labs on campus that are part of that group. And they were the ones who funded most of our collaborative robot arms and some of our smaller systems that we use to look at kind of industry problems, manufacturing problems, and those kinds of things. And we are moving forward looking at developing a model for partnerships with institutions and with companies where we can do either in-kind things. We've had a few companies who have literally just sent us robots and said, here, please use this. as well as partnerships for training, for doing that kind of reverse co-op piece that I've been talking about. And we're trying to figure out what that relationship looks like, but we should have that figured out by hopefully the end of the summer, and then we can start offering effectively membership in the RoboHub in exchange for training or kind of using our expertise, maybe having some time in the RoboHub to do experiments, et cetera, those kinds of things.
Great. How many staff members, equivalent full-time members, are tied directly to the RoboHub?
So currently we have 4 and a bit, a little over 4 full-time equivalent members, or staff members rather, because we have myself and then Alex, the humanoid specialist that I talked about. We have a full-time technician that just started this month, and we have a postdoc who just started this month who's dedicated to the RoboHub itself. But we also have a support team from our PIs and the other professors that use the space, because we have up to 40 or 45 faculty members and their postdocs and their technicians and their lab managers working with us as well. But dedicated to the RoboHub, there's 4 of us.
Are you also doing curriculum development for the students, for new students onboarding?
Yeah, so that's one of the things we're working on throughout the summer, actually, is figuring out both the safety piece and the training piece. So for doing the onboarding, figuring out what training they need to work with particular systems, ROS workshops, which we're partnering with ClearPath to kind of come and run several kind of beginner ROS workshops as well on campus. And we're going to start running almost like a lunch and learn session every week or couple weeks. In the fall, we're hoping to start that, where we're going to look at the practical aspects of doing robotics. And those will be open to everybody, undergrads, staff, graduates, everybody.
How do you manage usage of RoboHub in terms of scheduling? What are the hours of operations? Do students have access after hours?
So currently, because we are still working through all of the safety training aspects, somebody with access to the room, which is restricted to employees of the university, so faculty and staff basically, and postdocs, has to effectively let you into the lab. But if you schedule a time, we've had experiments happening anywhere from 8 a.m. down to 8 p.m. really, and some on the weekends. We've had events come in on weekends and things. So it's really dependent on the needs, because we also host a lot of tours for main campus, for the dean's office, for the department, etc. Whether it's government officials coming in or industry or visiting professors, etc. And a lot of those things are actually also critically important, because part of what we're doing is trying to make those connections. So we have kind of cooked in our mandate that we want to be able to enable those connections and enable those kinds of tours and things to happen as well. So there's no kind of hard and fast rule about access. It's really more about figuring out how much time you need and what time you actually need in the RoboHub, because we have a lot of simulation tools, we have a lot of remote access tools and things. So most of the time, if you're not physically working with a robot, you don't necessarily have to be in the RoboHub itself.
And this also ties a little bit to the next question about the external access. So one question is, what are some of the ways to connect or meet up with mechatronics students interested in co-founding robotic startups, and also if you have already any process for access to RoboHub for external students, or you are still working on that?
So in terms of general access, we don't have a process yet. If you go through one of the PIs, one of the professors who's involved directly, then it's fairly easy to get access, because effectively they're kind of sponsoring you to use the space. We do have a lot of undergraduate research assistants from first through fourth year. We have some co-ops starting soon. I think we have 1 or 2 in the fall. We have visiting students from Egypt actually coming. in the fall as well, who have been sponsored by one of the PIs to basically come and do their final year capstone projects in the RoboHub, hosted by the university. So really right now it's a question of figuring out what kind of relationship that you want to have with the RoboHub and with our professors, and then just kind of finding a way to make that mean you can work in the RoboHub with the robots, etc. We are planning on making slightly more formal structure, at least on the industry side, less so on the academic side, so that we can say, you know, as part of your membership, you get to send 4 people to reverse co-op every year, and you get, you know, 3 days in the RoboHub or 2 days in the RoboHub, whatever it is. So we're working on that, and we should have it kind of by the fall, in the fall at some point. But yeah, as of yet, we don't have a kind of a defined process for doing that.
One question back to your tools in RoboHub. Have you ever taken the Q drone outdoors? I hope you say what I hope you say, but I would like to spin it a little bit. Which of the robots you actually can use outdoors, and what's your, if you are flying any drones outside, what are your challenges there, given all the permits, or, you know, do you have any extension of the RoboHub outside?
Yeah, so we have most of our ClearPath robots are indoor or outdoor. So the Warthog, the Huskies, the Jackals. The Ridgeback is on holonomic wheels, so it doesn't go outside. But those are all on the ground, so there's no real rules about that, other than, hey, can I drive in your parking lot, your gravel pit, your farm, your etc. When it comes to the drones, the Q drones, we have 2 spaces on campus, both indoors, that we fly them. So we have the RoboHub and we have the flight arena in one of the older engineering buildings. And then the outdoor drones that we have a couple of matrices, and we're getting a Arion Sky Ranger, I think it is, that we do use outside, and those need a lot of kind of paperwork to be generated to actually do that reliably and safely. Particularly because of the new Transport Canada rules. You have to kind of register the drone, you have to do, you know, if you have to get registered as a pilot with them, and there's a lot of different things that we're going through, and we're trying to figure out a way to streamline the process right now, so that anyone can run their code on the drone, but one of our registered, licensed, etc. Pilots, for lack of a better term, we'll just have to kind of accompany you and the drone and be in charge of the kind of remote takeover and all that kind of stuff, so that the students themselves, whether they're visiting or otherwise, don't have to go through the whole process. They just need to be accompanied by someone who has, so that we don't have to jump through all those hoops for every single person who's gonna want to put code or a sensor or hardware or whatever on one of our outdoor systems. I
would like to thank you for really great and interesting presentation, and thanks to everyone who joined us today. I would like to again mention the upcoming workshop of the Mechatronics education community that will happen September 27 to 28 at Lawrence Technological University. So if you are interested, visit the Mechatronics education website for the details. There are some already, but more information will be coming in the next couple of weeks. Thank you very much for joining us today.